Hi everyone, this is Mrs. J, and today we're going to be graphing simple rational functions using transformations. So before we get started, I have a quick warm-up for you guys. Please complete the following t-chart for the function f of x equals 1 over x and graph the function on your axis. Please pause the video and hit play when you're ready to check. All right, so go ahead and check your work here. So this is what the parent function of our rational functions look like. So 1 over x is kind of the most basic rational function that we can create. So a few things about rational functions which you see in this graph. First, you'll see that as x approaches positive infinity, so as you're moving to the right, because you're dividing by x, whatever your x value is, you are getting closer and closer and closer to 0. But we're never quite reaching 0 because if you think about it, it's impossible to divide by anything and get 0. So you're going to keep getting infinitely closer to your x-axis, but you'll never quite reach it. And the same thing happens on the negative side. So as your x values become increasingly small, like very, very negative, like negative 100, again, these numbers are going to be very, very close to your x-axis. They'll almost be 0, but not quite, and it will never, ever, ever touch your x-axis. So for that reason, rational functions will have what are called asymptotes. So this one, it has a horizontal asymptote at y equals 0. So this horizontal asymptote it really describes our end behavior. So what is your graph getting really, really close to as x approaches positive and negative infinity? But you'll see that we also kind of have that same type of behavior around your y-axis. So you can see as your x values get really, really small, your y values are getting really large because dividing by a fraction is like multiplying by the denominator. So that's why you can see like 1 divided by 1/4, you get 4. So the smaller your x value is, the larger your y values are going to get on the positive side. However, you'll see from our graph that we're getting really close again to our y-axis, but we're never quite touching it. And that's because x cannot equal 0. You cannot plug 0 into this function because then your denominator would be 0. So you can plug in any number that's like super, super, super close to 0, but you can't ever actually plug in 0. So the same thing is happening on the negative side. Like you can plug in negative 1 over 100, but you cannot plug in 0. So we have another asymptote here. So we have a vertical asymptote, which is also a feature that you will see with rational functions. And for our parent function, the vertical asymptote is at x equals 0. And again, the reason for that is because our domain is restricted. We cannot plug in 0 to this function because your denominator cannot be 0. So today you're going to see this really common pattern of a function that looks kind of like this. It kind of looks hyperbolic, so like two kind of parabola-shaped graphs. Oftentimes they're on opposite quadrants, not always, and you'll see that we do have horizontal and vertical asymptotes. All right, so let's start by talking about what the definition of a rational function is. So a rational function is a function that is a ratio of two polynomials. So p of x over q of x, and of course where the denominator, that polynomial cannot equal 0. Now, as you saw in our warm-up, rational functions have vertical asymptotes. They can have one or maybe more than one, and then they will oftentimes have a horizontal asymptote, or sometimes they'll have what's called a slant asymptote or an oblique asymptote if it's a more complex rational function. But asymptotes are a real key feature of these types of functions. So today we're going to be graphing our rational function from transformational form, which looks like this. So a times 1 over x minus h plus k. So it's the same rules for any function with our transformations. This is a shift left or right in the opposite direction. This is a shift up or down. And this is a vertical stretch or shrink. And then if there's a negative out front too, that would be a vertical reflection. Here, if we have any type of horizontal stretch or shrink, just remember you do need to factor it out from x. And then we can just treat it as a vertical stretch or shrink because we can always pull it out of the denominator. So really what we're going to do is we're going to transform the points 1, 1 and negative 1, negative 1, which you saw were two coordinates from our warm-up. And we're also going to transform the asymptotes from our warm-up, x equals 0 and y equals 0, in the same way that you would transform coordinates. And then we can graph just using those rules of transformations. Okay, so let's give this one a try. So here you can see we have the two coordinates from our parent function, 1, 1 and negative 1, negative 1. So we're going to look at the new function and we're going to determine the transformations we see. So here I only see one horizontal transformation and it's a shift to the right one. So if I want to move my coordinates to the right one, I'm going to add 1 to them. So I'll do x plus 1 here. And then I see two vertical transformations. I see a vertical stretch by a factor of 3. So we're going to do 3y. And then I also see a vertical shift up 2. So I'll add 2 to all my y values. And this will give us our transformed coordinates. So here we have 2 and then 0. And then here we have 3 times 1 plus 2. And 3 times negative 1 plus 2. So negative 1. So the same rules that we applied to our coordinates, we can also apply to our asymptotes. So for any vertical asymptotes, for the parent function is at x equals 0, but just like the rest of the function is going to shift to the right one, so is our horizontal asymptote. So we'll add 1, and our horizontal asymptote will now be at x equals 1. And then for the vertical asymptote, for the horizontal asymptote, the stretch doesn't really change it at all. If we multiply 3 to 0, it doesn't change it. But the shift up 2 will change it. And just like the rest of our graph is going to shift up 2, so will our horizontal asymptote. So we just add 2 to y equals 0, and our horizontal asymptote is at y equals 2. So we can start by plotting our asymptotes. So we have x equals 1 and y equals 2. And then we can plot our transformed coordinates. So we have 2, 5. And then we have 0, negative 1 right here. Now, to make the rest of our graph, it's also going to be really important that we find any x and y intercept. So we already have our y-intercept, but now let's see if we can find the x-intercept. So of course we find an x-intercept by setting y equal to 0. So we do want to know exactly where our graph is crossing. So we could say 3 over x minus 1 plus 2, and then just solve for x here. And then we have negative 2x plus 2 equals 3. And then we'll subtract 2 and divide by negative 2. So we have an x-intercept at negative 1/2, 0. So something right around here. So we'll just estimate right there. And then if we wanted to, we could always plug in another value somewhere over here to get a little bit of a more accurate graph. So a good number to plug in could be maybe 4. Let's plug in x equals 4, just to get an extra coordinate to make our graph a little more accurate. So we have 4 minus 1 plus 2. So this gives us 1 plus 2, which is 3. So I did pick 4 strategically because it looked like it'd be easier for us to simplify. So we have that extra coordinate of 4, 3. So I'll plot that on our graph. And then I'll zoom in a little bit on the graph. So we have something that looks like this. And there you go. So to describe the domain and range here, so our domain and range is essentially going to be all real numbers except for our asymptotes. So for our domain, it's going to be everything except for 1. So let's do this in interval notation. So negative infinity to 1, and then 1 to infinity. And for our range, it's going to be everything except for our horizontal asymptote, which is 2. So negative infinity to 2, and 2 to positive infinity. Okay, let's try another example together. So let's start with our horizontal transformations. I see that our graph is going to be shifted to the left 3. So I'm going to subtract 3 from all of our x coordinates. And then I see 3 horizontal changes, or sorry, vertical changes. I see a vertical reflection, a vertical stretch by 2, and a vertical shift down 2. So we're going to do negative 2y minus 2. And this will give us our transformed coordinates. So this gives us negative 2 and negative 4. And then here we get negative 2 minus 2, which is negative 4. And then here we get positive 2 minus 2, which is 0. And we're going to apply these same changes to our asymptotes. So here we'll subtract 3 to shift it to the left 3. And here, again, the negative 2y is not going to, or the negative 2, when we multiply it, won't affect our asymptote. The only thing that will affect a horizontal asymptote is a shift up or down. So when we subtract 2, we get that shift down. So here's our horizontal asymptote at y equals negative 2, and here's our vertical asymptote at x equals negative 3, right here. And we can plot those transformed coordinates that we have. So here we have negative 2, negative 4, and then we have negative 4, 0. So here we do have our x-intercept. It would be nice to know what our y-intercept is, and of course we can find our y-intercept by plugging in 0 for x. So do negative 2 over 0 plus 3 minus 2. So this gives us negative 8 thirds, which is just negative 2 and 2 thirds. So we can estimate that here. So it's somewhere right around here. So we know our graph is doing this on the right. And if we want, we could plug in an extra point on the left to give us a little bit of a more accurate graph, or we can just say, okay, we know that it's going to look something like this. So I think for this graph, we have more than enough to have a pretty accurate graph. And then for the domain, it's going to be all x values except for a vertical asymptote, which is negative 3. And then for our range, it's everything except for our horizontal asymptote, which is negative 2. And there you have it. Okay, let's do one more together. So here, there hopefully is something that you notice in the equation that we need to take care of first. We do need to factor the 2 out from this 2x plus 4 before we determine what's going on. So we have 1 over 2 times x plus 2 plus 3. So it's really important that we do that, because you could look at this and say, oh, this is going to the left 4, but it's actually only going to the left 2. Now this 2 up front, we could treat it like a horizontal shrink by a factor of 1/2. We could keep it horizontal, or we could treat it as part of that a value. We could just pull out the 2, imagine this is 1/2. So this is a vertical shrink by a factor of 1/2. And I will always opt to treat it as a vertical shrink rather than this horizontal stretch or shrink. So the only horizontal thing that we see happening is this shift to the left 2, so we'll do x minus 2. And then we have that vertical shrink by a factor of 1/2, and then it's going to be shifted up 3. So this gives us negative 1 and negative 3. And then here we have 1/2 plus 6/2, so 7/2. And then here we have negative 1/2 plus 6/2, so 5/2. And then our vertical asymptote will be shifted to the left 2, so x equals negative 2. And our horizontal asymptote will be shifted up 3. Okay, let's see what our graph looks like. So we have x equals negative 2 and y equals 3. And then we have our transformed coordinates. So we have negative 1, 7/2. Right here. And then we have negative 3, 5/2. So we can see which quadrants our graph are in, but it would also be nice to have our x and y intercepts. So let's find those. So let's start with our x-intercept. So I'll replace y with 0. So 1 over 2x plus 4 plus 3. So negative 3 equals 1 over 2x plus 4. And we'll multiply both sides by 2x plus 4. So negative 6x minus 12 equals 1. So x is negative 13 sixths. So a little more than 2. So right around here, again, you're just going to have to estimate on your graph. So we have a graph that looks like this. So you can see it's getting really, really close to our asymptotes. Again, never quite touching them. And then let's find our y-intercept. So we'll replace x with 0. Oops, 2 times 0 plus 4 plus 3. So we have 1/4 plus 12/4, so 13/4. So again, it's right around here. So it's just above 3. So again, you just have to kind of estimate where that is on your graph, and we get a graph that looks like this. Again, I know it looks like my graph is touching our my horizontal asymptote, but just imagine it's getting really, really close, but never quite touching. Okay, last really quick, let's do our domain and range. So our domain is everything except for negative 2, and our range is everything except for positive 3. There you have it. All right, so at this point I'm going to ask you to pause the video and give this one a try on your own, and you can hit play when you're ready to check your work. All right, go ahead and check your work here. You do need to do that first step of dividing out the negative 1 from your binomial in your denominator. So it gives you negative and then x plus 1, and you can actually just pull the negative out front, and you could treat it as a vertical reflection. So here we have a shift to the left 1, which is why I subtracted 1 from our coordinate and our x and our vertical asymptote. And then we have a vertical reflection and a vertical shift down 4, which is why I also subtracted 4 from our horizontal asymptote. Here's the transformed coordinates. I also found the x-intercept, our y-intercept we found here, and then here's our domain and range. So now we're going to talk about how we can graph a simple rational equation that isn't quite in that transformational form, but we would like it to be, so we're going to learn how to rewrite it. So this doesn't always work, but for a simple one like this, we can do it. So to rewrite it, we're just going to actually do some long division. We're going to divide our numerator by our denominator. So we'll do 3x minus 4 divided by x minus 1. So we get 3x minus 3, subtract, and then we're going to write it, we're going to write our function like this. So we have our remainder over our divisor, and then our quotient is just 3. So usually we'd write it as like 3 plus negative 1 over x minus 1, but I just flipped the order so it looks more like our transformational form. All right, so now let's transform some coordinates. So we know that our original ones are 1, 1, negative 1, negative 1. And then here we're going to be shifting our graph to the right one. So we'll add 1 to all of our x values. And then we have a vertical reflection, so negative y, and then up 3. We also know that our vertical asymptote is going to shift to the right one. So it's going to be at x equals 1. And we know that our horizontal asymptote is going to shift up 3, so that's going to be at y equals 3. So I'll plot those on first. And then we can find these transformed coordinates. So here we get 2 and 0. And then here we get negative 1 plus 3, which is 2. And here we get positive 1 plus 3, which is 4. So we have 2, 2, and 0, 4. So we have our y-intercept. We still need to figure out what our x-intercept is. So let's set y equal to 0. Now we can do this with our transformed function, but if we go from our original function, so we set y equal to 0, if you think about it, you have to ask yourself, well, when is a fraction equal to 0? When the numerator is equal to 0. So in this case, we really just need to set the numerator equal to 0. and solve. So we get x equals 4 over 3. So it's at 4/3, 0. So again, it's just past 1, so you just kind of have to estimate where that is on your graph. So we get a graph that looks like this. Oh, and our domain and range, sorry about that. So our domain is going to be everything except for +1. And our range is going to be everything except for 3. And we are all set. All right, so why don't you pause the video and give this one a try on your own, and when you're ready to check, you can hit play. All right, go ahead and check here. So you do need to do the long division to figure or to rewrite your equation in that transformational form. When you do that, you get this, which you do need to take that extra step again of factoring out the -2. So now you can see the -2 is outside, and then this becomes x minus 2. So this graph is going to the right 2, and then there's a vertical reflection, vertical shrink by 1/2, and down 2. So here's my transform coordinates. You can see where the asymptotes are. Over here you can see I found my y-intercept and my x-intercept and my y-intercept, and then down at the bottom are the domain and the range. All right, so the last thing we're going to do is we're going to see if we can look at a picture of a graph and see if we can create the function. So when I'm doing this, we're going to create the function in transformational form. The first thing that we can do is we can look at the asymptotes, because we know that the asymptotes tell us how much we've shifted left, right, up, or down. So we can see that we have a shift. So we have a shift to the right 4, because our vertical asymptote is at x equals 4. And then we can also see that we have a shift down 3, because our horizontal asymptote is at y equals 3. So we can start our equation by saying a over x minus 4, because we're shifting to the left 4, and then minus 3 for the down 3. But now I still need to find this a value on top. I need to figure out what my vertical stretch or shrink is in addition to any reflection. So to do this, I can substitute x and y with 6 and -2, and then we can solve for a. So I'll add 3 to both sides. So our a value is equal to 2. So that means our function is just 2 over x minus 4 minus 3. All right, here's the last example for this video, so please pause it and give it a try, and you can hit play when you're ready to check your answer. All right, so go ahead and check your work here. You can see that our graph was shifted to the left 1 and then up 5, and then you can substitute this point that we know, -4, 6, to help you find our a value, which was -3. All right, and that is all for today's video. Thank you so much for watching.